In section 3.9, number 35, we are given the fact that function value f of 1 is 5, and we're given the graph of the derivative, and we're supposed to use a linear approximation to estimate f of 0.9 and f of 1.1. So first of all, f prime of 1 is 2, according to the graph. So again, that's a picture of f prime, not f. And the fact that f prime of 1 equals 2 means if x increases from 1 to 2, so if x goes up by 1, f will increase by about 2. That's part of what the derivative means. So that is the rate of change of f when x equals 1. We can interpret it sort of like a linear slope, except we realize that 2 is the approximate change in f when x increases by 1. And by the time we get to x equal 2, there will be a new instantaneous rate of change, but it's an approximation. And that actually means we can prorate that if x increases from 1 to 1.1, so instead of increasing by 1, it increases by 1/10, then f will also increase by 1/10 of 2. So it will increase by about 2/10. Right? So if y is expected to increase by 2 for an increase of 1 in x, then it will increase by 1/10 of that for an increase of 1/10 in x. And similarly, if x decreases from 1 to 0, if we go in the other direction, if we move to the left on the function, then f will decrease by about 2, according to this derivative value. So the derivative being the approximate change in the function when x increases by 1. If we go in the other direction, decreasing x by 1, then the derivative is the negative of that change. So instead of increasing by 2, we expect f to go down by about 2, which again means if x decreases from 1 to 0.9, then f is going to decrease by about 1/10, right? X decreases by 1/10, then f will decrease by about 1/10 of 2 to be 0.2. So buttons up your undershirt. F will increase from 5 to 5.2 approximately, or in this case, f will decrease from 5 to about 4.8, because we're told that f of 1 is 5. Okay, now that's sort of thinking about it from a very practical, let's just think our way through this. Part A says use linear approximation, which basically boils down to the same thing, but now that we have sort of the basic idea under our belts, let's just recall that f of x can be approximated by its tangent line equation when you're near the point of tangency. Whoops, not x equal a, for x near a. Right, so again, remember, this equation is the tangent line to f at x equals a. We can also call it the linearization of f. So we think about the fact that if we zoom in on f, in this case near x equal 1, it's going to look like a tangent line. It's going to look like a straight line, and that straight line actually will be the tangent line that it resembles. Okay, so in this case, a is equal to 1. That's our x-coordinate of the point of interest. So f of x can be approximated by where we were at f of 1. We were at 5. And then we're going to change by the amount of the derivative prorated for however far from 1 we go on the input. So, for example, f of 1.1, I'll do that one first, is approximately f of 1 plus f prime of 1 times 1.1 minus 1. So what does that mean? F of 1 we're told is 5, and then we're going to take the derivative value of 2, but we're going to prorate it. Instead of x increasing by 1, x is only going up by a tenth. So my y value of 5 is going to increase by a tenth of 2. That is 5 plus 0.2, or 5.2. And f of 0.9 is roughly wherever we were at f of 1, plus we're going to increase by the slope, but prorated for the amount of change in the x. So f prime of 1 is roughly how much change we'll see in f if x increases by 1. We're going to actually let x decrease by 1, and we're going to prorate the change accordingly. So we've got 5 plus 2 times negative a tenth, or 5 minus 0.2, or 4.8. So that matches what we got up above. So again, we're saying instead of running along the function f, we're running along its tangent line to estimate function values. All right, now part B says, are your estimates in part A too large or too small? So note to self, if we look at this derivative function, it is decreasing. So f prime is decreasing, which means f is concave down. So I don't know what f looks like. I'm totally making this up. But let's suppose here's x equal 1. And let's say I'm blowing this up. So here's 1.1 and here's 0.9. And I'll just put a little lightning bolt here. Okay, so this is f, not f prime now, but I'm just making up what f looks like. All I know for sure is it's concave down. And so you see when the function is concave down, the tangent line lies above the curve. So here's, let me just make a little more space here. Here's f of 1 equals 5 that we were told. And here's 5.2. And on the tangent line, here's 4.8. And we are saying that the 5.2 is an estimate for the function f value, but we're on the tangent line. And the value 4.8 is an approximation of f of 0.9, but notice both of those are above the function f. So since f is concave down, the tangent line lies above the curve, which means approximations are over estimates. Our approximations are on the tangent line, and those are above the actual function values. So they are too large.